Hello everyone, this is again Groundwater Part 3. Here we're going to talk about the aquifer and aquitar. So let's look at those. What do you by aquifer? If you remember last time we talked about permeable materials and impermeable materials. Permeable are the one that allow the water to go through, and impermeable are the one that does not allow the water to go through. So an aquifer is a permeable rock strata or sediment that transmit and allow the groundwater to move freely, like in sands and gravels. So for example, this one here is permeable. So we say that this rock here is called an aquifer. Same thing here. This rock allows the water to go through, so it's also an aquifer. But the rock that is impermeable is qualified as aquitar. So an aquitar is an impermeable layer that prevent the water to move freely. Like for example, in clay, look at clay for example. Actually, it's not low porosity. It's high porosity and low permeability to be precise. So you might probably wonder so the water here we can understand comes from rain right here. So let me draw this here. So the rain falls, it goes all the way here. Can the water go through? No, because this is impermeable. So once it gets here, it flows and for build up and gets higher until it gets to the water table. Okay, but he cannot go through. But how about this groundwater here? How it gets here? To understand how this water gets here, we need to extend our rocks. If I extend the rocks here, I can extend all the way to here. And remember, the rocks are not always horizontal, they're slanted. So this goes like this goes like this. And you have something that looks like this. I can even create like a 3D, but again, I don't want to complicate the whole thing here, but you can see what I'm doing here, right? Okay. So now if a rain fall here or here or here, it definitely will not go through. I mean, it will not go through this because it's impermeable, but it will go through here. And this will be filled up. And that's how we get the groundwater here because of this area here called recharge area. This is called recharge. That's where you have water coming through from rain and going all the way to here. For this one, rain falls here or here or here, it goes to this groundwater right here. So this is called unconfined aquifer, meaning that above it there's nothing above it. It's like the earth's surface. But the confined one is the one that is confined within specific layer. It's usually below an aquitar, and maybe you have another aquitar right here. So it's confined in one specific place. So how groundwater flows in in the groundwater right here. So basically, as I said, we have a recharge area right here. So this is where the water flows and move under infiltration. Same thing here, and go and um, and finally the water move through here, and finally it get to the river. That's where you have what you call discharge. Same thing here, recharge, discharge, recharge, discharge. Okay. Now, if you'd like to understand how the water flows underground, because you're at the surface, you cannot be able to see, you cannot see how the water flows. If you are here, for example, and that's underground, you cannot see how this water is flowing. By the way, this is the water table, and from here to here is groundwater. Okay, and this is the well right here. So the question, how do we know how the water flows underground? If your example on the earth surface right here, for example, let's say, for example, I extend this a little bit up like this, for example, okay, and make it like a little high like this. And if I ask you if rain falls here, where that rivers or runoff flows, of course you would say the river flows like this. Why? Because the river or runoff flows from high elevation to low elevation. You can see it. High elevation to low elevation. You know the elevation of this. Let's say, for example, this is 200 feet. This is 100 feet. The water go from 200 to 100. But how about the groundwater? How do you know where the water flows? This way or this way? To know the flow of the groundwater and where the water is flowing and where the groundwater is flowing, we need to know the elevation of the water table. Let's say, for example, we have a water table as like this, for example. Let me extend this a little up. Let's say you have all this groundwater, for example. In this case, if I ask you where the groundwater flows, from 1 to 2 or 2 to 1, of course, it has to go from 1 to 2 by gravity. It goes like this, not 2 to 1, 1 to 2. But how do you know that this point right here is high elevation than this point? So that's what we're going to try to find out. We try to find the elevation of this point right here of the water table. Because if I know the water table elevation, if I know this one is high elevation and this one is low elevation, I can safely say that the water goes from 1 to 2. Okay? So let me clear this out. So how can you do this? So the first thing, you have to measure the depth to water. So you drill a well, for example, up to here. Let's forget about this. You drill a well up to here, okay? And you use an electric water level sounder. So you drop it in the well here, for example, all the way here until it touches the water. And once it touches the water, this probe has 2 electrodes in here, and it's lowered into the water, into the well, okay? When the probe touches the water completes the electric circuit, and once this happens, this triggers the light or buzzer at the surface. So you have a sound here. When it's touched the water, you have a sound on your device, and you read on this instrument the depth record here. You can see the depth recorded once the buzzer starts to. Once you hear the buzzer, you can read the depth of the well. Okay. So the depth is known by this instrument. So we have the depth 10 feet. Okay. Now let's assume that the sea level is right here. The elevation by definition is the height above sea level. So remember, I'm looking for this height from here to here. Let me use another color here. The elevation of this point, for example, or this point right here, is how high this point above sea level. So I'm looking for this number, number right here, from here to here, this elevation. So I have the depth of the well, which is 10 feet, and how determined? Determined by this electric water level sounder. So I get my 10 here. Also, I should know the elevation of this casing right here, the top of the well. So if you know the elevation, which is basically, this elevation is from here all the way to here. Let's say it's 30 feet. And that's something you can determine on the surface. The elevation of this point is the height from sea level all the way to here, that's 30 feet. So if you know the height or the elevation of the casing of the well, the surface, and you know the depth, how much is the elevation of the water table here? So to find this, you need to do 30 minus 10 to get this. So the whole thing here, which is 30, minus the depth, which is this, which is 10, gives you this height, which is the elevation of the water table. In our case, 30 minus 10 would be equals 10. 30 minus 10 is 20 feet. So the elevation of the water table here is 20 feet. So the elevation of the water table here is 20 feet. Okay? So imagine I have another well right here, and I find the elevation of this water table here, for example, to be, let's say, 5 feet. If I connect the dots, I have 20 feet here, and I have 5 feet. So the elevation here is 20 feet above sea level, and the elevation, I'm sorry, it should be, sorry, not 5, it should be, let's say, 30 feet, because from here to here, let's say it's 30 feet, no, 30 feet, I'm sorry, let me give you an example, because this is not, it's very, all right, let's, for example, find here, let's say, for example, the depth we found here is how much? We find 20 feet. And let's say, for example, here in this well right here, we find only 5 feet, for example. And I ask you where the water flows now. Of course, it flows from here to here. So now I'll be able to know the water flowing from this location to this location, because I know the elevation of this point, the elevation of this point, the water flow this way. Okay? All right. So again, imagine, for example, let me choose another example here. Let's say the elevation of the well casing is 240.50. Let me take this off. If the elevation is 240, here, for example, the elevation of this is 240 right here, from here to here, and the depth of the water is 5.15 meter. What is the water table elevation? All you have to do is use this equation. Water table is to go from here to here. This elevation from here to here is the elevation of the whole thing from here to here, elevation of the casing, minus the depth. So elevation minus depth, we have 240 minus 5.15, it gives you 235.35 meter. That's the elevation of the water table. Let's look at this now. Forget about these numbers here. Let's forget about this number. This is the example previously, but let's say now the elevation of the casing is 585. So let's say the elevation from here to here is 586.3 meters, and the depth of the water of the well from here to here is 10.33. To know the elevation of this from here to here, you do the whole thing minus the depth, which gives you 586.3 minus 10.33. So basically you have to do 586.3 minus 10.3. Okay, and you'll be able to find the elevation of the water table. And that's the example I just have here. This is an example where we have the elevation right here, 582 from the sea level right here. all the way to here. Again, I gotta repeat this. So from here to here is 586.3. That's the elevation of this point right here. The depth is from here to here. That would be 10.33. And I'm looking for the height of the water table from here to here. So again, you do this minus the depth, and you'll be able to get the elevation of this, which is 575.90 meter. All right, now once you know the elevation of different points, let's say, for example, the elevation here is H1 in this well right here, and this is the elevation of the water table. Remember, this is water table here. So let's say, for example, this water table here is, let's say, 200 meter high. And the elevation here of the water table, again, I'm talking about elevation of water table. You know how to do it. Let's say here we have, for example, 100 meter, the height. Again, the height from the sea level. How high is this point? So if you would like to find the gradient or slope of this location from H1 to H2, you use this equation. So we have hydraulic gradient equals H1 minus H2, H1 minus H2 divided by the distance. The distance between the two locations is this one right here, from here to here. So let's say the distance, for example, is 10 meters, for example. So I have the height of the water table is 200. Let me put 200 here, meter, minus the elevation of this water table right here, which is 100 meter, divided by the distance between the two, which is 10, and that give me 200 minus 100 is 100 meter, divided by 10 meter, and that give me 10. In this case, 10 meter per meter. Again, if you have, let's say here, miles, for example, if you have miles here, I'm gonna put here miles here, miles here. In this case, would be 10 meter per mile. That's even better, because if you have meter per meter, they will cancel each other. It will not make sense that much. But what is 10 meter per mile? That's even better, because if you have meter per meter, they will cancel each other. It will not make sense that much. But what this means, it means that every mile you go from here to here, if I start from here to here, every mile you go this way, you're going to go up 10 meters. So if you start from H2, if you start from H2, as I go along distance D by, let's say, 1 mile, I have to go up 10 meter high. Okay? And of course, as you go like this, if you connect the dots, you'll be able to get to H2. Every mile you go 100. Every mile you go 100, and so on and so on. And this is basically called the slope of the groundwater, of the water table. So the slope is important to understand the flow of the water. Meaning, if you have, let's say, for example, H1, H2, distance here, for example, is, let's say, 10 miles. So I'm going to use the same example. I'm going to put 200 here. I'm going to put 100 here. So the hydraulic gradient would be, using the equation, would be 200 minus 100 divided by 10. That will give me 10 meter, I'm sorry, 10 meter per mile. If I have another example, let's say, for example, I have something like this. I have, let's say, I'm going to start with 200 also here. And here, let's say I have 190 This means the difference between this and this. Look at this. The difference between this and this is 100. But here, 290 is only 10 only. And let's say that the distance, let's stop it here. You know what? Let's take this off. Let's put the point here, H2 here. This is H1, this is H2, 190, for example. And let's give the same distance, same as this one right here, 110 miles. Okay? So 100 gradient in this case here would be same thing, 200 minus 100. Forget about this, as I said here. Forget about this. We're going to keep the same distance from here to here and from here to here. The only difference that this one is steeper, this one is gentle. So here we have 200 minus 190 divided by 10, and that'll give me 10 meter divided by 10 miles, and that will give me 1 meter per mile. So which one is very steep? Of course, the one that says 10 meter per mile, but this one is only 1 meter per mile. What does it mean? It means that for in this case right here, every, let me do it here. For this one right here, every mile you go this way, that's 1 mile. You go 10 meters, sorry, 10 meter up. 10 meter per mile means for each mile you go up 10 meter. For this one here, for each mile, you go only 1 meter. 1 meter per mile. I'm sorry, this is 1 meter, sorry. So you can clearly see here that this is steeper. Look at this, steep, and that's gentle. And that's what you call the slope or hydraulic gradient. And in this case, in which case the water will flow faster. Of course, here. The groundwater here will go fast in here, but here the water will go slowly because of the slope, because of this slope right here. So the higher the slope, the higher the hydraulic gradient, the faster the water moving. Okay? That's very important. And that's the purpose of this equation right here that gives you an idea about the slope and also the flow of the groundwater. Now, let's try to understand the reason behind the understanding or mapping the water table. Why do we need to know how high is the water table? As I said, the water table elevation is important. Let's look at this scenario right here. Imagine we have a town, and we have Dubois House, the Clearwell School right here, Sunny Farm, and so on and so on. This is Route 66, for example, and so on and so on. So for Dubois, the elevation of the water table, again, remember, I'm talking about the elevation of the water table. Let me just put this in context here to understand what I'm talking about. This is the ground surface. This is a surface right here. This, for example, Dubois House. And here we have the groundwater right here. So this, the elevation from the sea level all the way to this point right here is 104. That's what you have, 104 here. So that's how high is the water table. So for the school, for example, or Clearwell School, it's only 102. From here to here, for example, is 102. And from here to here, the water table elevation here is 104. I hope you understand how you connect this with the real, I hope this put things in context. Is 104. I hope you understand how you connect this with the real, I hope this put things in context. This is school, for example. Anyway, so those numbers here, they indicate the elevation of the water table in meters. So we have here, again, that's how we denote the water table. We have to know the land surface elevation. We have to know the depth of the water, and you do this minus this, you get the elevation of the water table. Anyway, so we have our results right here. Like the land surface, if you go back to the land surface again to help you understand this, this is the land surface, for example. If I say, if the water falls, for example, here, rain, let's say, the rain will go like this. Okay? So if I would like to look at the elevation, this point, for example, here, I'm talking now about the elevation of the surface now, not the water table. This elevation, for example, this one are the same. Okay, so I'm gonna connect them with one single line. This elevation and this elevation are the same. I connect them with a line. Let's say, for example, this elevation here, for example, is, let's say, this is an example. Let's say this is 200, for example, and that's 150. So of course the water will go from 200 to 150. The line you see here are the line that connect the same elevation. 200, 200, 200, 200, 150, 150, 150. The water will flow, if you have water, for example, rain, for example, or runoff, it will flow like this. It will flow perpendicular to this, what you call contour lines right here. Those are called contour lines. Okay, that's a law. If you have contour lines that connect the same elevation, the water will flow perpendicular to these lines that connect the same elevation. Same thing for the water table. If you have, for example, 104 here and 104 somewhere here, and 102 here and 102 here, we can connect them, and then you'll be able to draw the line that indicate the flow of the groundwater, which is this, perpendicular to this line that connect the water table that have the same elevation. Well, here we don't have that much data. We have 104 here. Imagine, for example, we have another 104 here. So what I'll do, I'll connect the 104. Let me use another color here. Let me use, let's say, purple, for example. 104, 104. I'm gonna connect this with this. Imagine you have 104, of course, for example, here, for example. I'm gonna connect 102. Let's say we have another 102 here, for example. I will connect this with this. 100 with 100, 98, 98, 96, and 94, for example. Once you have this line, which I have already drawn in the next slide right here, those red lines right here are the line that connect the water table that have the same elevation. For example, this line here has 102 elevation, this one has 100, and so on, so on. As we know, the groundwater will flow perpendicular to this lines right here that connect the water type with the same elevation. So anytime we draw those, they're called, by the way, flow lines. Those are called flow lines. So, okay. So the scenario here we have here is that imagine the school has oil leaking in the basement right here. And once you have drawn these lines along with the flow lines, if this basement of this school leak the oil, then where this oil will move in the groundwater? Well, it will move like this. It goes like this and it goes like this. So this is the path this contaminated water will flow to. It goes like this. So which groundwater will be affected? Of course, ironworks factory will be affected. A riverside also will be affected because it's in the path of the water that's contaminated. Because the water flow like this, from high water elevation to low water table elevation, this contamination will move like this and pass by this factory and also with a riverside house. So if this river house, for example, use well for domestic use, for example, then they have to they have to be warned against this leak that happened here in Clearwell School, for example. So let's say, for example, Clearwell School declared that there is a leak in the oil. So right away, if you know this pattern of flow lines, then a riverside house should be alerted that there is contamination. There's a possibility for their water to be contaminated because the water is moving, the contaminated water will move towards their house. And if I ask you, will Dubois House be affected? No, because the water table here, which I will draw, for example, here as uh, this is the house of Dubois, this is the school, for example. Dubois, for example, has 104, and because the contamination happened in the school right here, and because the water is going this way, so definitely the water will not go up. So Dubois house groundwater will not be affected. This is another example of mapping the water table. You can have, for example, different cities here. And let's assume that a truck, for example, or for example, somebody, oil, for example, or let's say gas station, for example, their storage of oil start to leak, and people around here, they want to know where this water, contaminated water, will move to. Is it moving this way, or this way, or this way? And that's why we need to know the water table elevation. So once you know the water table elevation, you connect the line that have the same water table elevation. Once you draw those dark lines here, then you should be able now to draw the flow line, and flow lines are perpendicular to the line that connect the water table with the same elevation. So we have this, we have this, we have this. So because this is going this way, so the area that will be contaminated is, because we have the contamination starts here, and because the groundwater is moving this way from high water table to low water table, all this area will be contaminated. Okay, the numbers here are not like whole number of the time, but it's, you can draw those lines so that you can connect the point that have the same water table elevation, and finally draw the flow lines that are perpendicular to these lines. This is another example. You can practice if you'd like to see how you. This is another example. You can practice if you'd like to see how you connect the dots. You can see, for example, this is water table elevation right here. And here we can connect, you can create lines that connect the point water table that have the same elevation. In this case, because this, if you go, let's say by tens, we start 150. 150 is between 151 and 145. So you go a line here, another line for 140 here, 130 going like this, 120, and so on and so on. Once you draw those lines, it will be easier for you to draw the flow lines like this that are perpendicular to the contour lines. So it's very important to have an idea about how the water flows under the ground, although you cannot see it. All right, now comes what you call Darcy's Law. So how groundwater moves, we can measure the groundwater movement using Darcy's Law, which is a measure of the volume of the water Q that flows through an aquifer. It's like almost the same thing as discharge for the water. If you think about it, if I draw here, for example, let me draw here water. This is water flowing, for example, here. Okay. So the motion of the water or the speed of the water depends on the gradient. Why? Because, for example, if you have this gradient like this, for example, between these 2 points, as opposed to something like this. So we have scenario number 1, scenario number 2. Again, this is water table right here, and that's water table. Of course, the one that has high gradient is where the water will flow faster and more. More water flowing here than here. And that's what you have what we call hydraulic gradient. So the amount of water flowing through a specific section of the aquifer depend on the gradient. The higher the gradient, the more water flowing. But also it depends on what we call hydraulic conductivity, which take into account the permeability of the aquifer and viscosity of the liquid. Because if the liquid is more viscous, it moves slowly. If it's less viscous and more fluid, it moves faster. Okay, so the equation for this, the amount of water flowing through groundwater is given by this Q, the amount of water flowing, equals K, which is hydraulic conductivity, which is linked to permeability and viscosity, and times area times hydraulic gradient. I can write this as K equals K, right here, K, times A, and we know that the hydraulic gradient is equal to H1 minus H2 divided by D. If I call this, for example, H1, H2, and this D, so that's the hydraulic gradient. If I plug this here, right here, that's I. So KAI, which is this one, I, again, is hydraulic gradient, and you get this equation. K equals K times A times H1 minus H2 over D. So let's see how can you use this, the amount of water flowing through a certain area using the equation. Very simple. So what is the quantity Q of the groundwater flowing horizontally? So it's flowing like this. It's flowing almost horizontally like this. Through a section of 2 by 2. Let's say you have a section here, 2 by 2. So if I draw this box, for example, that's 2 by 2, 2 feet by 2 feet. I need to know how much water is flowing through this section right here, through this area, 2 by 2. Again, I'm not talking about the volume actually. It's let me clear this again. I don't need to confuse you here with this because we're talking about the area. So my area would be this. So this is the area here. It's actually a square. That's 2 by 2. What I need to know the amount of water flowing through here. And that's Q. Okay? So it's easy to find. Basically, they give you the area right here. 2 by 2 square means that the area here is 2 times 2. So this area right here, oops, let me use another color here. This is the area, 2 by 2. This gives you area, which is 2 times 2 right here. So it represents area. K is given to me. K equals 180. K equals 180 feet per day. It's given to me. So all I have to do is I'm going to plug K by its value right here. That's K. And also I was provided by hydraulic gradient, which is 1 feet per 1,000 feet. Sometimes you have the same unit, feet per feet, 1,000 feet per 1,000 feet. And I would be this. And once you have this, you multiply 180 by 2 times 2 by this, and that will give you, if you multiply the number here, we get 0.72. And feet, if I look at the units, I have feet per day, per means divide, times feet, that's feet square, feet divided by feet, feet divided by feet, and now this cancel. Feet times feet square is feet cube divided by day, and that's my unit, feet cube per day. Meaning that every day we have 0.72 feet cube of water flowing in a day through a section of 2 by 2. That's what it means. All right, your turn. Question: using the law of Darcy, calculate the quantity Q of groundwater flowing horizontally through a 3 by 3 square section of an aquifer. The hydraulic conductivity K is 250 feet per day, and the hydraulic gradient is 0.02. Again, if you look here, there's no unit because they can be feet per feet sometimes. Usually they use feet per feet or meter per meter to cancel the thing. But the reason why I show you meter per mile to explain to you the meaning of that hydraulic gradient. All right, let's look at this question, so you can pause the video and you can solve the question by yourself and check if you are correct or not. Well, here we have the answer. We have K. First, you have to put the equation Q equals KAI. K is given to you. Where is it? Right here. K is given to you. Area is also given to you. Is 3 by 3, so 3 times 3, which is 9 feet square. And also they give you the I, which is hydraulic gradient, which is 0.02, which is 9 feet square. And also they give you the I, which is hydraulic gradient, which is 0.02 right here. You multiply everything, you get 4.5 feet cube per day. Same thing for the other question. The other question, you have the equation here, K equals KAI. The K is given to you, which is 12 meter per day, right here. They are also given also the cross section, the area, 1.5 by 4, that gives you 6. Then they give you also hydraulic gradient, which is 0.05, and finally you get your answer, which is 0.36 meter cube per day. Thank you.